Hello class, Mr. Sutton here, and today we're going to be talking about complex fractions and permutations and combinations. So first we're going to do some complex fractions here. There's no notes to go over, we just have some examples. Because there are no really new concepts here, we're just applying some concepts we've already learned to some new material. So the idea here for the complex fractions is you want to make your numerator one fraction and your denominator one fraction. So right now they're separated with this subtraction. We want to make separately the numerator and the denominator one fraction. So I'm going to start with the numerator. In order to make this one fraction, we need to have a common denominator. So our denominators right now, we can rewrite this 1 as 1 over 1. So our denominators right now are 1 and x. So our common denominator, or least common denominator, is going to have to be x. So I'm going to multiply by x over here. So then I'll have x over x minus 5 over x. Now I'm ready to combine this into one fraction because we have a common denominator. So that fraction would be x minus 5 over x. So I can go ahead and write that as my new numerator. And then the denominator, we can go ahead and make that one fraction as well. Here we have denominators of 5 and 25. So our least common denominator is going to have to be 25. We'd have to multiply this fraction by 5 over 5 to get that. So that would be 5x over 25 minus x squared over 25. Now we have a common denominator, that's 25. So 5x minus x squared over 25 would be what we have once we combine them. So that is the first step, is to get the numerator and the denominator as one fraction. The next step then is to rewrite this as a division problem. Remember that fractions are the same thing as dividing, right? Like if I have 2, 10, that's the same thing, or excuse me, 10 over 2, that's the same thing as 10 divided by 2 equals 5, right? So a fraction is the same operation as division. So I'm going to rewrite this as this numerator divided by this denominator. Okay? So we're going to do that. We're going to have x minus 5 over x divided by 5x minus x squared over 25. So once we've done that, if you recall, when you are dividing fractions, like if I have 1/2 divided by 3/2, let's say, remember the way we do this is we change the operation to multiplication, and then we flip this fraction over here. And then we just multiply. So we multiply, or dividing is the same thing as multiplying by the reciprocal. So then this would become 1/3. So we're going to do that. So we're going to change this into multiplication. And then we need to take the reciprocal here. So 25 would now be the numerator and 5x minus x squared in the denominator. So now we can multiply across. So we'd have x minus 5 multiplied by 25, and then x multiplied by 5x minus x squared. Now notice I didn't actually multiply anything, I just combined it into one fraction. That's because you are likely going to have to simplify this. It does say fully simplify, so this answer is not going to be good enough. We're going to have to simplify it. So multiplying would just create some extra work for ourselves because then we'll have to factor again later. So we want to go ahead and factor what we have here. The one piece that's not factored already is this 5x minus x squared. And what I'm going to do with that is we have a GCF of x, and so I'm going to factor out the x, and I'm also going to factor out a negative so that this becomes x minus 5. So both of these would change signs if I factor out a negative x. It'd become negative 5 plus x, which I'm rewriting to x minus 5, switching those around so that now we can see that these factors cancel. So then we are left with 25 over negative x squared, which I'm just going to bring that negative out in front. And that is our final answer. Nothing else to simplify there. All right. So to recap the kind of steps here, first step is make the numerator and the denominator one fraction. And then rewrite that fraction as a division problem, rewrite it as a multiplication problem, and then multiply and simplify. Okay. So let's go ahead and take a look at this next problem. We want to follow the same steps we did in the last problem. So we want to first make the numerator one fraction. So we want to combine these. So right now our denominators are x and x squared. If we want to combine these, we have to have a common denominator. So that common denominator is going to be x squared. So multiply by x over x. Now we have a common denominator, so we can go ahead and add the fractions together. So x plus 1 in the numerator, x plus 1, and x squared the denominator. So this is going to be our new numerator for our larger fraction. Now we want to go ahead and do the same thing for the denominator, rewrite it as one fraction. And right now our denominators in this are 9 and 3x. So our least common denominator here is going to have to be 9x. We're going to have to multiply this fraction by x over x and this fraction by 3 over 3. So then we have x over 9x plus, that's going to be a 3 over 9x. So then we have x plus 3 over 9x. So that is going to be our new denominator. So this turns into that. And now we have this as one fraction over one fraction. We can go ahead and rewrite it as a division problem, like I did in the last one. So it's x plus 1 over x squared divided by x plus 3 over 9x. And then the way we do division problems with fractions is we change the operation to multiplication and take the reciprocal. And then we can go ahead and multiply these now. And again, I would not actually multiply them, just combine them into one fraction because you're probably going to want to cancel some things first. And the only thing it looks like we can cancel here is the x with one of these x's down here. So we have, and I'm going to go ahead and distribute now as well. So we'd have 9x plus 9, and then distribute that one x squared plus 3x. And that's all we can do for that one. So that is our final answer. So again, process is we combine the numerator and the denominator into one fraction. And then once we've done that, we rewrite it as a division problem, then as a multiplication problem, and then multiply and simplify into our simplified fraction. Now we're going to talk about combinations and permutations. Difference between a combination and a permutation. A combination, the order does not matter. A permutation, the order does matter. So, and here are your formulas. This is for combination. And this is for permutation. Some things to remember, the exclamation point is a factorial. So the way we do that, it's like 5 factorial. You just multiply by each integer, counting down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. So now we're going to go ahead and move to Delta Math and look at some examples using combination and permutation. And the reason why I wanted to look at these on Delta Math is because I wanted to show you that Delta Math has these formulas for you. Here's the combination formula right here and the permutation formula right here. So you do not actually need to calculate any of that stuff by hand for these problems because it is all in the calculator on Delta Math. So I'm going to show you how to use that. So for this one, you get permutations and combinations in the same problem set, so you don't know which one you're going to get. So the hardest part is going to be determining if it is a permutation or a combination. So the thing to remember is that permutations, the order does matter. Combination, the order does not matter. So you have to think through the scenario and try to determine if the order matters or not. So for this one, Miss Bell's mathematics class consists of 8 sophomores, 12 juniors, 14 seniors. How many different ways can Miss Bell create a 4-member committee of juniors if each junior has an equal chance of being selected? So for this one, the order does not matter because the committee doesn't have specific roles. So like let's say John, Sally, Sue, and Ben were selected. That is the same exact group if you did Ben, Sally, John, and Sue, right? If you selected those same 4 people in a different order, that is still the same group. If there were specific roles and she was assigning them to specific roles, then all of a sudden the order matters because, you know, you select someone into one position is different than if you select a different person in one position. But for this one, the order does not matter, so that's going to be a combination. So we use this formula, and we are selecting, N is going to represent the total that we're selecting out of. So we're selecting out of the 12 juniors because she's selecting a committee of juniors. So N is going to be 12. And then R represents how many we are selecting. So that would be 4 in this case. And then see, Delta Math spits out our answer over here. So that would be 495. Just going to type that in, submit. So order doesn't matter, only choosing from juniors, so that means N equals 12, and we're going to use the combination. So N choose 4, that is how you pronounce this, is N choose 4 equals 495. So let's look at another one here. John has 6 different flags that he wants to hang on the wall. How many different ways can the flags be arranged in a row? So first thing we need to decide is if this is permutation or combination. Does the order here matter or not? This one, I think pretty clearly the order does matter. He's literally trying to determine how many different ways he can order the flags. So that would have to be a permutation. So permutation, formula, and then we have 6 different flags that we're ordering in 6 different ways. So in this one, both N and R equal 6. Right? We have the 6 flags and we're putting them in 6 different positions. So out of 6 flags going into 6 spots, N equals 6 and R equals 6. So that would be 720. Ranging all 6 flags out of 6. If we had 6 flags, but we were only hanging 4 on a wall, then it would be like 6 permute 4. And that is how you pronounce this. This 6P6 is 6 permute 6. So that's worth noting as well. But in this case, we are permuting all 6 of them. So it would be 6 permute 6. All right, let's go ahead and look at this next one. There are 9 different actors auditioning for the roles of Larry, Curly, and Moe. How many different ways could the roles be cast? So again, the first thing we need to define or determine is if the order matters here or not, which in this case, the order does matter. And this is one that I think confuses some people because you might think the order does not matter if 3 people are cast, and this it doesn't matter, but because there are specific roles that they're being cast for, it matters in which order that those 3 people are cast. So what I'm saying is, let's say Ben, John, and Rob are cast for this part. You might think that the order does not matter because you might think that if John, Ben, and Rob are cast, it's a different order, but it's still the same 3 people cast. But the thing is, they're being cast into specific roles. So the order does matter because Ben being cast as Larry, John being cast as Curly, and Rob being cast as Moe is different than John being cast as Larry, Ben being cast as Curly, and Rob being cast as Moe. So when you are choosing people but assigning them to specific roles, that is always going to be a permutation. Because those roles mean that there is an order to what you're doing. Okay, so this is a permutation. So we want to click the permutation function. And then there are 9 actors here. So N is 9 being cast into 3 roles. So it's going to be 9 permute 3, which is 504, it says. So I'm going to submit that. So order matters. Actor A is Larry, actor B is Moe is not the same as actor A is Moe and actor B is Larry. So there's an order to this. So you're arranging 3 parts out of 9 actors. So we use permutations. 9 permute 3 equals 504. So let's look at another one here. There are 15 people on a basketball team and the coach needs to choose 5 to put into a game. How many different possible ways can the coach choose a team of 5 if each person has an equal chance of being selected? So this is similar to the previous one, but different in the fact that the 5 people being chosen are not being assigned to specific roles. It does not say that. He is not placing people into specific positions on this basketball team. It doesn't say anything about, assigning a point guard, shooting guard, small forward, power forward, center, anything like that. There are no specific roles in this basketball team. If each person has an equal chance of being selected. So that means there is no order to this basketball team. If you choose 5 people, and then if you have a different 5 people, but it's the same people in a different order, then those are the same exact team. So this would be a combination, and it's out of 15 people. And so n equals 15. R equals 5 because we're choosing 5 of them. So 15 choose 5. So that is 3,003 different possibilities here. So let's go ahead and submit that. Order doesn't matter because it's a team without distinct positions. So we're using combination. So that is 3,003. All right, if you have any questions about any of this, make sure you are asking for help during class, and have a good day.